Hello, hello. Welcome, everybody. Welcome to this webinar. Hello, Joe. How are you? Good. Can you hear me? Yes.
Yes.
Okay, cool. Fantastic. So welcome all of you guys. And so this will be a webinar this morning regarding acoustic fundamentals. So my name is Nicolas Poitrenaud. I'm from NEXO Engineering Support, in charge of supporting all our customers around the world, very much involved in the education programs. So I've been working for NEXO now for 5 years. I was a freelance sound engineer from the past, and now just a full-time job at NEXO. And I'm very pleased to welcome also Joe, who is in charge of the Asian territory. Joe, how are you?
Good. I'm very good. How are you?
I'm good, very good.
So yeah,
So,
so I'm in charge of Southeast Asia, India, and Australia. Actually, we have another colleague who takes care of Northern China, and so I see that many participants today are actually from India. I'm sure I've met some of you a couple times, and I'm really looking forward to coming back to India to see all of you again. But in the meantime, let's have a great webinar today with Nicola.
okay, thank you very much, Joe. So before we start, just a few words about how you can maybe participate to the webinar. You have different windows available. There is a chat window. So in the chat window, you can discuss with all the people. You can also discuss with Joe if you want. You can also discuss with me, but it will be a little bit difficult for me to participate to the chats. But if you have any question, there is a Q&A window also available, so at the bottom of the screen. So feel free to ask any question and to interrupt the webinar by writing question on this window. And Joe will be able to interrupt me, and we'll look at the windows constantly, and I will try to answer all of your questions during the webinar. Right. So this is the first slide. Let's go and ask our question about what is the sound. So the idea of this webinar is to talk about sounds, but from practical approach. We need also to discuss a little bit about the science of sound. So maybe as you know, but what the name acoustic means. So acoustic, has just look at the definition just before this webinar. So acoustics is coming from a Greek word. I think it's something like acoustikos. And acoustics is a branch of physics that deals with sounds. Okay, so it's very simple. Acoustic is taking care of the sound. So this is the science for sound. But as you may know, as a sound engineers or a system engineer or sound technicians, we know that sound is a science, but sound is also perceptions. Okay, so we need to take care of these two different branch of the acoustics. If I took at the first things, the physical phenomenon, we can talk about the sound by just explaining that the sound is coming from a source. So it can be my voice, for example, can be any instrument, can be a loudspeaker. So in that case, we talk about source radiation. This is musical acoustics or electroacoustics. And then the sound is traveling through the airs. And so when we talk about sound through the airs, we need to take care of the environment. And maybe the sound is striking any surface. So we talk about reflections, we talk about room acoustics. So in reality, when we talk about acoustics, there are many topics that we can discuss regarding if it is direct sound, if it's reverberant sounds, if we talk about loudspeakers. So this is it's a huge topic. But we need also to consider the sound as a perception. Because if you discuss with a musician, for example, if you ask a musician what is a sound, he will not answer by saying that the sound is a waves. You know, he will talk about is feeling. Okay, so you can say that sound, for example, as a color. Okay, I don't know if you interesting in jazz, for example, you know, in jazz there are what we call blue notes. So they talk about blue notes. So sound is a color. So it's very difficult, but if we need to take care of these perceptions, because as a sound engineer, we need to discuss both as a technical, on the technical side, but we need also to discuss on the perception side. So we need to know a little bit about our ear anatomy, but we need to know also very much about psychoacoustics. Psychoacoustics is the category, the branch of acoustics that deals with perceptions. And we also should take care of the sociology and the ethnology of the people, because, for example, if we had to answer this very difficult question, which is what is a good sound, if you go to Europe, if you go to India, if you go to Japan, if you go to China, if you go to the US, nobody has exactly the same definition of what is a good sound, because the perceptions of sounds comes also from our own personality. Okay, this is very much related to the place we live, to what we used to listen, what kind of music we used to listen. So it's a very complicated question to answer. Anyway, so let's start with the physics. So let's consider the sounds as a physics. So as you may know, sound is a vibration. This is what you call a longitudinal vibration. And this vibration is being transmitted from the source through a medium. And most of the time, the medium is the air. So it goes from the source to the listening point. If I look at this analogy, I can say that the a sound, the vibration, is very much similar to a mass and a spring. If you look at the air, so air is composed of air particles, particles, sorry. But if you also push a pump, you can realize also that air is very much like a spring. So air is a mass and also a spring. And this is exactly what happened in the air, okay? It's not very easy to visualize because, as you can see, the vibration and propagation goes in the same way, okay? So we used to work with another analogy, which is more visible. This is the waves propagation in water analogy. So wave propagation in water analogy is this experiment. You just take a stone, and you just put the stone into waters, into a lake, for example, and you look at what happens. So what you see is you create waves, okay, and this wave is traveling through the waters. Let's have a look in details about these waves. So if I block the wave propagation, what I see here is that the waves, when it's traveling through the water, if it goes to a floater, when the waves cross the floater, then the floater is moving top and bottom, okay? So what you see in the movements of a floater is there is a cycle in time, okay? Because every milliseconds, every seconds, I don't know, the floater always goes to the same positions, okay? So it goes up, goes down, and then it keeps at the same position. So this is a cycle in time, and this cycle in time is called the periods. But if you look also, if you could freeze the water, if we freeze the water, what you can see here is that there is a distance between two waves, and this distance is always the same. So this is what we call the cycle in space, and this cycle in space is called the wavelength. Okay, and when then the last parameters is the waves is traveling at a speed, and this is the speed of the waves. Okay, so if I just summarize what we explained before, important value for us is the cycle of time. Cycle of time is the period. So we use the seconds to measure the periods. But we used to work with another value, which is called frequency. Frequency is the number of cycles in 1 second. So we use the hertz. Frequency is very useful because frequency is very much related to the pitch. Okay. We also use the spatial length of a periodic cycle. Okay, so this is what we call wavelengths. And the last parameter is the speed of sound. And as you may know, the speed of sound depends on the temperatures and the medium, the humidity of the air. For example, we used to say that the speed of sound is 342 meters per second. This is true for 20 degrees, okay? But it's less if you go to 16 degrees, and it's much more if you go to 25, 30 degrees, okay? Few words about speed of sound. Speed of sound is, if we compare speed of sound with speed of light, speed of sound is very slow, very slow. So as you may know, the speed of light is 300,000 kilometers in 1 second, okay? This is the fastest speed of anything, okay? We cannot go above that value. And the speed of sound is 0.3 kilometers per second, okay? So it's very, very slow. But once again, it's much more useful to get this equivalence and to say that 1 meter is equivalent to 3 milliseconds. So when I have to, for example, calculate any delays in my sound system, I can take this relationship is 1 meters of distance is exactly the same as 3 milliseconds in time, okay? Right, so let's participate to a first quiz. We talk about speed of sound, but the question is, if we say that the speed of sound is 342 meters per second, if I have to compare to something that I know, what is equivalent to the speed of sound, according to you? So we have 4 different answers, possible answer, if you can see my poll. So first answer is speed of Formula One car. Second answer is speed of aircraft. The third answer is the speed of ballets. And the last one is the speed of a very famous runner, Usain Bolt. So can we try to go to vote? So come on, guys. We have 25% of people voted, which goes to 31. Okay, I will end the poll now and share the results with you. So speed of a Formula One car is the speed of a car. So speed of a car, as you may know, the speed of a car is something, I think the maximum is something like 350 kilometers per hour, okay? So this is not, the sound goes faster than the Formula One car. Speed of a ballet goes faster than the sound. So the good answer was the speed of the aircraft. Okay, so we can say that the speed of sound is more or less the same as the speed of an aircraft. Okay, very nice. Go back to presentation again. So we talk about sounds, speed of sound. Let's carry on and let's discuss now with other important value. And this one is very important for us, is the wavelengths, okay? You may know, we said that the wavelength is the the distance traveled by the waves, sorry, during one period, okay? So basically, this is the speed of sound multiplied by the periods, but we used to take this formula is the speed of sound divided by frequency, okay? So wavelength is the same of speed of sound divided by frequency. As you may know, these are the different frequency that human being is able to hear. So the biggest wavelength, so the smallest frequency is 20 hertz. The highest frequency is the 20,000 hertz, so 20 kilohertz. And I would like you now to calculate the wavelengths of a 20 hertz sound. So a new question for you guys, but I invite you to answer. what is the wavelength of a 20 Hertz sound? So remember, speed of sound is 340 meters and frequency is 20 Hertz. So what is the speed of sound in that case? So we just have to take 340 divided by 20. 340 divided by 20 is exactly the same as 34 divided by 2. And 34 divided by 2 is 17 meters. Okay, so the good answer was the last one. So this is the majority of people that goes to 17 meters. So thank you for participating to the polls. And now let's summarize with you guys. So you're right, 20 Hertz is 17 meters, okay? 17 meters, if I compare, is the size of a building. So it's a huge, huge value, okay? 17 meters is the lowest frequency. If I multiply the frequency by 10, then I will divide the wavelengths by 10, okay? So if I try to compare 200 Hertz with the size of any shape, it's 1.7 meters, and 1.7 meters is more or less the size of human being. Okay, so if I had to say that wavelength is the size of the wavelength, I can say that the size of a 20 Hertz sound is a building. The size of a 200 Hertz is the size of human being. The size of a 2000 Hertz is the distance between my two ears, okay, so this is the size of my head, and 20,000 Hertz, so 20 kilohertz, the size is the size of my finger, okay, so it goes to a very big value building up to a very small, which is the width of my finger. Right, so let's try to memorize and let's try to keep this value in mind. This will be very helpful for the future. Carry on with, once again, important value. So let's talk about powers and acoustic pressure. So as you may know from the past, when you receive, technical writers from any sound engineers or from any bands in tour, they used to provide any power available. So the requirement was to give such a power for a number of people. What does it mean in reality? The power is the ability just to generate energy, okay? But we don't use that value anymore because power is not really interesting, because power is related to the efficiency of the loudspeakers. If we, for example, ask and provide 1,000 watts or 5,000 watts to the power amps, we cannot guarantee that we will get 5,000 watts in acoustic power, because the acoustic to electrical efficiency is not very good. It's around 10%, so this is true for any loudspeakers. Can go a little bit more, can go up to 17, 18%. But the efficiency is not very good. So it's not really good idea just to give any powers for requirement. What is a better idea, and this is what we use now in the tenders or in the technical riders, is we talk about acoustic pressure. Acoustic pressure is the pressure that is applied from one air particle to its neighbor. Or we can also say that the acoustic pressure is the pressure that is applied by the loudspeakers to the air, okay? So the value goes from very small value up to bigger value. But as you can see here, we know that this acoustic pressure is just moving with the time. So we have different value because this is variable pressure. And we need to take care, because when we talk about acoustic pressure, we can talk about the maximum. So the maximum is what we call the peak pressure. So this is the maximum value, and this is what you see here. This is the peak. But peak is not really interesting for us, because our ear is not very sensitive to the peak. We prefer use like an average of the energy. And the average of the energy is what we call the RMS. So RMS means root mean square. So this is a mean of the energy. And this is the RMS, okay? This is the average of the signals. So in reality, we have also to define something which is called Crest Factor. So the Crest Factor is the difference between RMS level and the peak level. If I go back, this is the crest factor. Okay, so this is the difference between the maximum and the average. And in reality, we know some of famous crest factor. For example, if I take a sine wave, I know that the crest factor for a sine wave is 3 dB. I know also that the crest factor for a peak noise is more or less 10 dB. No? There is 10 dB of difference between the maximum and the average. And for music or speech or anything, I don't know what is the crest factor. Okay, and this is the beauty also of the sound is we don't know what will happen in the futures. Okay, the crest factor can vary from 6 dB, can be less, sometimes can be 2 or 3 dB, can be very small value, up to 20 dB. So I would like now to share some example with you, guys. So there is, we will have some different possibilities. So different sound example. So this is the first one. Okay, this is the first track. Now let's listen to the second track. Okay, so two tracks very different. Okay, it's like a night and day and black and white, so they are very different. And the question is this one. So can you try to answer the next question? Is a question about crest factors. So we've heard two music tracks, and in the two tracks, which music track has the biggest crest factor? Okay, so is it music track number 1 or music track number 2? So just as a reminder, the crest factor is the difference between RMS and peak. Okay, so currently, interesting because the majority, so I will end the poll and share the results with you. So the majority goes to music track number 2, and this is not the good answer, okay? The good answer was music track number 1. So once again, let's visualize that. So just to make sure that this is clear for you. When we talk about crest factor, let's go back to presentation. So the crest factor is the difference between the RMS and the peak. Okay, RMS is the average. This is the waveform, sorry. So this is the waveform of the first track. So you can see the peak here is the maximum of the value, and like the blue colors is the average. So you can see that the average is not very high, but the peak is very high. So if I compare the distance between the average and the peak, okay, so this is, you know, here is the RMS, okay, and here is the peak, and this is the difference between the two, okay. If I give that example, so the next example is now with other tracks. So you see this is highly compressed, and if I again compare the RMS, so the RMS is here, okay, and the peak is here, okay, so it's more or less the same. In that case, I can say that distance between RMS and peak is maybe 2 dB. So the crest factor is very small. So the good answer was the 1. Biggest crest factor is very much similar to also dynamics, okay, so this is the very difference between the lowest value and the biggest value. So not to say that one is better than the other, once again, not to say that the first track is better than the second track, and be the opposite. These are absolutely two different sounds. Sometimes some musics are heavily compressed because they want to push the level, they want to emphasize the loudness. And just for us, as a manufacturer point of view, we must provide the headroom, and our system must be able just to get every kind of music with different crest factor. And I must say that this is the difference of consumers equipments and professional equipment. Consumer equipment sometimes are not very good just to provide such a very big crest factor. So you see that when you try to push on this equipment, it's very difficult just to get the level. And this is very much different with professional equipment. So they have to provide any different crest factor available. They have to work for every any sounds, any music. Okay, let's carry on, and let's move to the next slide. Okay, cool. So important value. Again, we never use pascals as a unit for pressure. We used to work with dBSPL. dBSPL means sound pressure level. So this is a unit that you can calculate using that formula. Okay, so P is the pressure in Pascal. So if you get that formula, you can display any value in dBSPL. What is much more useful for us is to remember the scale at the right side of the screen. What we call 0 dBSPL, 0 dBSPL is meaningless. This is what we call threshold of hearing. And the threshold of hearing, to get the threshold of hearing, you need to get, you need to go to the doctors and get this headphone that plays very, very low level sounds. When we talk about silence, for example, if I go in a room, very isolated rooms, I close the windows, I don't have any noisy neighbors on any side, then you can see the value. The value is around 40 dBSPL. So silence is more or less 40 dBSPL. Conversational speech, so if you talk to anyone, it's around 60 dB, 60, 70 dB, okay? If you go, for example, to any concerts, then it can go up to 100 dB. And you see the maximum is what we call the threshold of pain. Threshold of pain is, for example, a driller. A pneumatic drill can be also engine of aircraft. So if I go above that value, then I can damage my ear. So I need to take care of that value. So I would say that the loudest sound is around 130, and the less loud sound is around 30 dB. 30 dB is really something which is silent. So the question is this one: if I measure 40 dB SPL, and if for me is silence, it means that there is not a good relationship between what I measure and what I hear. And the question is why I measure 40 dB SPL for silence. And the answer is what we call perceptions and psychoacoustics. So in perceptions, in psychoacoustics, what I realize is my ear is not very good to hear the low level, okay? For low frequency, I'm not very good to hear low level. And this is exactly the same for high frequency. So what does it mean? It means that if I had to measure the sounds, the unit dBSPL is not really appropriate, because I need to make it more linked to reality. I need to give a relationship between what I measure and the real world. So I need to apply these weighting curves to my measure. So we have 3 different weighting curves that we currently use. The one is what we call the dBA. So you can see in dBA that we have to attenuate the sounds but up to 40 dB, for example, at 40 Hz. And as we increase the value of the sound, then you see that the weighting curves, the filtering that we apply to the measuring is more linear, okay? So we used to apply these weighting curves for a level that goes to 20 to 55 dB SPL. We also have to use the B weighting. We should use the B weighting curves if we measure level from 55 to 85, and we should use DBC for high level, for level that goes to 85 to 140 dB SPL. So I will go back later in these different weighting curves. Let's now carry on and go with the phase. So phase is extremely important in our, you know, in acoustics. Why phase is extremely important? Because phase explains many phenomena. And why it explains many phenomena? Because it is based on this different experiment that we can visualize on the screen. But the definition of phase is the shift in degrees between two signals. Okay, so this is the delay. So this is the difference, the time differences between two signals in degrees. Why we use degrees? Because phase is using a mathematical definitions. Okay, so we talk about a cycle. So and we know that when we get a cycle, it's just very similar as if we turning on a circles. Okay, around the circle. So this is why we use degrees. And we know these different things. We know, for example, if we get two signals with 0 degrees of phase, so they are perfectly aligned, perfectly synchronized, then we can do the summation of two values and we multiply the value by 2. And when we have 6 dB of summation. So this is what you see on the left side of the screen. We have the blue signals, we have a red signal. And if we do the summation of blue and red, then we have twice the value, okay, plus 6 degrees. So this is perfect summation. If now I shift the phase and goes up to 90 degrees, then you can see that when I do the summation, it's no more a very good summation. So it's less than 6 dB. In that case, this is 3 dB more, okay? If I shift the phase and go to 120 degrees, there is no summation. So this is a very important value. Two signals shifted by 120 degrees, they don't sum together. Okay, so this is exactly the same level. And this case is very well known. This is what we call the out of phase. So when we have two signals out of phase, then you can see that we lose everything. Okay, so there is no more sound when they are out of phase. We also used to visualize these different results using this diagram. So this is a very interesting diagram. What you can see is a circle. Okay, so this is the phase. The phase it goes from 0 degrees up to 360 degrees. Okay, so this is the phase shift. And the green colors give you the signal summation. So when it's green, it means that we still have a good summation. The very good summation is, for example, when you go from 0 degrees up to 38 degrees, okay? In that case, you see that it's still 5.5 dB, so it's very good summation. When we go up to 90 degrees, this is what we explained before, we still have a good summation, it's 3 dB. But then when you go from 90 to 120, we start losing some amplitude. We start losing summation because 120 degrees, 0 dB, and after 120, then we lose. So minus 6 dB at 150 degrees, and we lose everything. This is out of phase at 180 degrees. So this zone is very critical for us, okay? After 120 degrees, if we go more than that value, then we will cancel the sound. And we get exactly the same if we go on the opposite, okay? Because this is a cycle. So we talk about degrees, but degrees is not very useful. We said phase is a shift is a shift in degrees, but we never use degrees in reality. When we talk about signal shift, phase shift, we talk about delay. So the question is, how can I get the delays converted in degrees for phase? So we used to work with this formula. So this formula is very useful because it gives the conversions of a delay time in phase shift. Okay, so to get the conversion from delay to phase, you just have to multiply 360, so this is 360 degree, multiply by frequency, multiply by time. Okay, So let's do an exercise together. So we'll try to calculate different values. So you can see we have a delay. So the delay keeps the same. So we keep a delay of 1 millisecond. And I would like to calculate the phase shift at 3 different frequencies. So we have 100 Hertz, 500 Hertz, and 1 kilohertz. And let's check that together. So 36 degrees, as you can see, is a very small value. So what does it mean? It means that this will not really impact or change the summation. We still get this good summation. But if I get the same value and increase the frequency and go to 500 Hertz, you see that in that case, this is absolutely a disaster, okay? Because I'm out of phase, so everything is canceled in that case. And the last point, 1000 Hertz, then I will go to the cycle again, and now I will keep in phase. So very important for you guys, for a fixed delay value, phase shift is always more important in HF compared to low frequency, okay? So low frequency, if you want to have a very big phase shift in low frequency, you need to have a very big value of delay. Right, so let's carry on. I just look at the time. Okay, so we still have 10 minutes of presentation, then we'll do a short break, a coffee break, and move back to the next part. So the last part of the first topic is about perceptions. So we talk about physics, but we need to talk about perceptions also. I told you that when we talk about perceptions, we need to talk a little bit about ear anatomy. So interesting to see, if you look at the history from the past, people believed that ear was full of very small resonators, which resonated according to harmonic contents, okay? But in reality, this is not true. Regarding the research that has been done in the 20th century, so this is what we call ear anatomy. So here is very much similar to a microphone membrane, okay? So in reality, we have what we call the outer ear, and in the outer ear, we have the eardrums, okay, that collected the sounds, and the eardrums is like the membrane of the microphone. And so when you get the sounds from the microphone, it goes to a preamp most of the time, and the preamp is exactly the same as the middle ear. So the middle ear is composed of different ossicles. So the ossicles will get amplification, so they will amplify the sounds. And as you can see also, there is a ratio. So why? Because the middle ear is also like a compressor. So interesting to see that the middle ear is also like a compressor. The reason is that we have some different muscles, and the muscles are connected to the ossicles, and from time to time, if the level goes too high, then the muscles will just block the ossicles just to make the level goes down. So it works like a compressor. So this is very much similar to a compressor. So we have microphone, preamps, compressor, and then it goes to the converter. And the converter is the inner ear. So converter just converts the analog sounds into digital, okay? So we have these different, what we call the hair cells. So we have these very important hair cells that just convert the sounds into electrical pulse. And this electrical pulse goes to our brain. So we know very much how it works from the outer ears up to the middle ears, up to the inner ear, but it's very difficult to understand what happens from into the brain. So it's still like a mystery just to understand how the brain interprets or understand the electrical message. Anyway, if we go now much more not in the ear anatomy, but in the perceptions, once again, I go back to this, weighting curves that we had in very low level. These weighting curves are very much related to these curves that we see on the left side. So, for example, if I go to these red curves with a 0, so these red curves is called the threshold of audibility. So how can I read these curves? This is the level that I need to provide to make the sound audible. So at 1000 Hertz, this is very obvious. You can see that I need to provide 0 dB SPL to make the sound audible. But if I go to 100 Hertz, I need to provide around 38, 40 dB SPL just to make the sound audible. So when you see that the curve is going up, it means that I need to play louder just to make the sound audible. So this is true for low frequency, but this is also true for high frequency. And this is why we need to get this attenuation of the sounds when we use the dBA, because we cannot hear that value. But if I increase now the level, go, for example, up to 120 dB SPL, but you can see that it's more linear now. I need to provide 125, so it's only 5 dB more just to get the same sensation of pain. Okay, and this is the threshold of pain. And also I need to increase a little bit the value in the high frequency. So I don't need to provide bigger level when I play a very loud level. So this is why you can see that the curves on the right side is more linear, because our ear sensitivity is also much more linear. Okay, so these curves are very, very important just to understand how we get the perceptions of a level. So we used, for example, to talk about auditory field. So what is auditory field? If I join, for example, the threshold of hearing curves, so this is the threshold of hearing curves, so I will just make it more visible again. So this is the threshold of hearing. And if I join the threshold of hearing with the threshold of pain, then I can draw this, you know, these things. Okay, I will make it in red. And this thing is what we call the auditory field, because all the sounds inside the auditory field is the sounds that I can hear. If I go outside of the field, I'm below the threshold of hearing. So for example, going there, I cannot hear the sound. And if I go above the auditory field, I'm in the threshold of pain. So I feel like just blocking the sound with my fingers, okay? So this is the auditory field, and music program is inside this auditory field. So we take the biggest frequency response, the highest value for the low level and high level. So this is also the music field. If I look at the speech field is smaller. The reason is the speech doesn't need to go to very low frequency. With my voice, I cannot provide any frequency below 100 Hertz, so it's quite impossible. And I cannot also provide frequency above 8 kilohertz. So this is the speech field. So the speech field is really smaller compared to the music field. And this is the speech field here. Okay, you see it's smaller. So this is useful for me. If I need to provide any speakers or any sound solution regarding application, I don't need to provide very big value for speech. Okay, I don't need to provide very high frequency or low frequency. So I can go with smallest cabinets. I can go also with less cabinets. I'm not also. I don't need to use subwoofer because the speech auditory field is shorter compared to the music field. So ear damage and protection, very, very, very important topics. So as I explained to you before, so we have air cells in the inner ears, and these air cells, when they are damaged, this is damage forever, for your whole life. So most dangerous sounds, you need to take care and you need to protect your ears when you play. So you need to take care of the level. So be careful with the level. And as you can see here, the most dangerous sounds are the ones with no warning. It's the sounds that you cannot anticipate, because if you anticipate the sound, then you can reduce the level, you know, with the compressor of your ear. So always check that there is no one next to a speaker prior to playing sound. So never unmute with open faders fade out, unmute, fade in. Okay, so you take the fader, so you don't press the unmute buttons when you go. You need to just realize that when you operate a very big sound system, this sound system is very much similar to a weapon. This is a weapon, so this is extremely dangerous. So take care of the people. So don't play the sound with no warning. Go to very low level up to a high level. Be aware on respect F regulation on sound pressure level. So for example, in France, we cannot go up to 100. And it's not 5, it's 2 now, it's less. So 102 dB SPL is the maximum dBA. And always carry hearing protection in case you are at risk of being overexposed. So when we say risk of being overexposed is, for example, when you work on any installation. So you have to fly the system, you have to, if you are lighting guys, you have to fly the light. So you need to have your ear protection if you want to keep your ear safe for your for the future. So don't remember that your ear is your most important tool in your job. We carry on and talk about auditory masking. So auditory masking, as you may know, is if I play two sounds at the same time. For example, if Joe is talking in the same time than me, if we talk together, it will be very difficult for you to understand what we say. Okay, this is what we call the masking effect. So two similar sounds alter each other perceptions. Okay, but if the frequency range is different, then it will not be it will not alter the perception. So in other words, what we used to say is low frequency always alter the high frequency perceptions. Okay, so the low frequency will disturb the high frequency, but not the opposite. High frequency will never disturb the low frequency. So this is the masking in frequency, but we have also an auditory masking effect in time. What is the auditory masking effect in time? If two sounds coming in a window which is less than 50 milliseconds, then instead of hearing two sounds, you will hear one sound. So the first sound will mask the second sound. Okay, this is what we call the fusion zone. After that value, we hear what we call echo. Okay, so echo is above 50 milliseconds. And I will finish with a spatial localization, sound intensity. So you know, if you want to localize the sound in the horizontal plane, so spatial localization is a mix of sound intensity in left and right ear. So this is the difference of intensity between the left ear and the right ear, but it's also the difference of phase. So this is the difference of arrival time between left and right. And if you combine arrival time and sound intensity, then you can sensitize, you can summarize everything into these curves, which are called head-related transfer functions. So these are filtering curves that apply to the different sounds regarding left and right. And as we know these curves, this is something that we learn when we were babies in realities, then we can localize the sound between left, right, top, bottom, everything. Okay. If you want to go to more sophisticated or more advanced functions, like, you know, we used to say 3D sound. So 3D sound is a different example that you can hear with a headphone, for example. In that case, we use head-related transfer functions. So this kind of technology is called binaural technology. So if you go to binaural technology compared to stereo, so binaural is a much more advanced compared to stereo because you can localize the sound also on the vertical plane. You can have the sound going up, down, and also behind your head. So this is binaural. So we talk about fundamentals of acoustics regarding, you know, what is a sound, what kind of different, you know, units that we have to use. We talk about phase, we talk about levels, we talk about powers, wavelength. So we talk about many things. Now I would like to go more about the source radiation things. So I will share with you, so there is a presentation, but I will also practice NS1 so that you can visualize the acoustic phenomenon inside the software. So from time to time, once again, I will move from presentation to NS1. And I will first start with a few definitions. So these first definitions is about point source and line source. So as you may know, we used to make the difference between a point source and line source. And the first question is this one is, what is a point source? Okay, so to be very simple, what we call point source is source where energy is emitting from a single point. I mean, if I take any loudspeakers, if I take, for example, the PS15, PS15 is a point source. But in reality, this is a box cabinet with two drivers, but it will be very much similar if every energy was coming from virtual points inside the cabinets. And this point is called Acoustic Center. So in this cabinet inside, there is a virtual acoustic center, and we can admit that all the energy is emitted from a single point. Okay, this is what we call, this is why we call that point source. What is the consequence of that? Is the energy is spread over a sphere. Okay, so the energy radiated is spread over a sphere or a portion of a sphere. And the sphere is becoming bigger and bigger as the sound is propagating. This is what you see in the drawing. So all the energy, the power is spread on the sphere. And if I propagate the waves, then the sphere is bigger. And what does it mean? It means that if I look now at the surface, so this is a piece of the surface of the sphere. Every time I multiply the distance by 2, so I make the radius of the spheres 2 times bigger compared to the first positions. But the surface of the sphere is increased by 4. Okay, so I multiply the surface by 4. And what does it mean in terms of sound intensity? I can see that the sense and the energy, the sound intensity drops in relation to 1 divided by square radius, which is similar to -6 dB per doubling distance. So important point for us, when we talk about point source, we know that every doubling, every time we multiply the distance by 2, we lose 6 dB. Okay, so don't expect to have a big throw with point source. Okay, it's just looking at the physics. It's very difficult. Why? Because there are dispersions on the horizontal plane and also dispersions on the vertical plane. So, for example, if I try to look at level, and let's take the problem in the opposite. If I say I want to have 100 dB SPL at the mixing position, so this is the mixing position, so this is 100 dB SPL, and let's say I want to provide 100 dB SPL at the mixing position, and the mixing position is 32 meters. So what must be the level at 1 meters? So if I have 100 dB SPL at 32 meters, it means that at 16 meters, I need to provide 106. Okay, so if I have 106 meters at 16 meters, that it means that I need to have 112 at 8, 118 at 4 meters, 124 at 2 meters, and 130 dB SPL at 1 meters. Right, so we know, once again, point source lose -6 dB per doubling distance. let's visualize now what we call the directivity. So the directivity is the coverage provided by the source. You know what? Let's try to visualize the coverage of a PS15 on NS1. Okay, so let's try to make it more interactive. So I will jump to NS1 now. Okay, so this is NS1, and I'm going now to build a surface. So let's open Venue. Let's create, let's create a square of 20 meters by 20 meters. Okay, so this is the area, audience area, and I will take this PS15 once again. So let's grab this PS15 and put the PS15 somewhere in this area. And now let's visualize the coverage given by this PS15 in the area. So I will visualize two different frequencies and start with, for example, 100 Hertz. Let's visualize 100 Hertz. Okay, once, oops. And you see that at 100 Hertz, this is more or less omnidirectional. If I go, for example, 50, very, very omnidirectional. So important things is, once again, as long as the wavelength is bigger than the size of the source, then the point source will be omnidirectional. So remember, we said that 50 Hertz, if I look at the wavelength, it's 6.8 meters. So 6.8 meters is bigger than the PS15. So this is omnidirectional. But if I look now at different frequency, if I go, for example, at 2 kilohertz, so 2 kilohertz, once again, the wavelength will be smaller. Remember, we said 2 kilohertz is the size of my ear. Okay, so we see 17 centimeters. And if I look now at the coverage, you see that now is directive. So low frequency, a point source is always omnidirectional, and it goes directional, so it's directive when you go to the highest frequency. It's a matter of just comparing the size of the sounds, the wavelengths, with the size of a source. Now I would like to look at the coverage of 2-point source. Okay, so instead of using 1-point source, I will use 2-point source, and I will duplicate my PS15. So we have one PS15 on one side, okay? And let's try to duplicate this one on the other side, okay? So we have two PS15 which are very close together. And again, let's visualize the coverage at very low frequency. So let's go to 50 Hertz. So you see that 50 Hertz will not change anything. But if I go to 2 kilohertz, sorry, let's go to, for example, 400, then you see that the coverage is different. So why the coverage is different? Okay, and once again, I move, go 500 Hertz, 600. Okay, now this is 630 Hertz. So why this coverage is going different? So the answer, you can visualize exactly what happened to your systems by looking at the wave behavior of a different point source. So there is a very interesting website which is called Falstad. So Falstad is the name of the founder of the website. So it's just like very small Java application. So this is Java applet when you can look at different acoustic simulation. And if I go to interferences, so let's go to this website together. So the name is Ripple Tank. So you see the name of the website, falstad.com. If you go to Ripple Tank, then you will be able to visualize the waves emitted by the 1-point source. This is 1-point source, but what is important now to visualize is 2 sources. So we'll get 2 sources, and put two sources very close to each other, I will also make the frequency lower. And you see, if you visualize, if I get these two sources very close to each other, then everything is absolutely perfect. We still get the omnidirectional behavior. We still get this the circles. Now, if I increase the distance between the sources, then as you can see now, we do not have any more these omnidirectional behaviors. Let's try to make it more obvious, to be more visible. Let's get this, for example. So I just increase the space between the two, and you see that we have some zones here where we have no circles. Okay, so we call that zone a cancellation. So this is a cancellation. This is very much related to phase again. And this is called, in physics, this is called interferences. So we create interferences. Interferences means that in some zones we have summations, and in some zones we have cancellation. Okay, and these interferences depends on the distance, because if the sources are very close, then everything goes well. If I increase the distance, then you see that I create the interferences. But it will also depend on the frequency. If I get my source very close, if I increase the frequency, then you will see that we also create the interferences. So remember, the distance is the same as the delays, and the frequency is a frequency. So why do I have these interferences? It's because of phase shift. This is very much related to phase shift. So question is, why do we have phase shift? So let's visualize this behavior on my presentation again. So let's go there. So we have two identical point source, okay? One is the blue one, so we have a blue one, and we have a orange one. As you can see, if we put a microphone at that positions, we can see that the distance from the blue speakers compared to the orange speakers is different. The blue distance is bigger than the orange. So there is a distance difference from each source to observation points. And this distance is what we call is the green distance here. Okay, so this is the phase shift. And if we have a phase shift, then depending on the frequency, depending on this value, we can have cancellation. Okay, and this is what we see, and this is what we add in our experiments. 2 PS15 space by 50 centimeters at 50 Hertz is still omnidirectional because the phase shift is not big enough just to make a cancellation. But if we look at what happened at now 630 Hertz, you can see the cancellation here. So this is not good in that case because our coverage is not consistent. Okay. If I try to now increase the distance, so instead of having a very small distance and increase the frequency, I can keep my frequency of 50 Hertz, but make a very big distance between the two sources. For example, we have two LS18 two subwoofer spaced by 16 meters. So it could be, for example, a subs on stage left and the other on stage right. So sorry, front of house left and front of house right. Then you have exactly the same effect. Okay, now this is called power Haley effect in that case because we have very good level of subs right in the middle and nothing at that positions. Okay, so interference are not very good in terms of coverage. So we see that we can add interferences with 2 speakers, but if you have more than 2 speakers, if you go up to 3, 4, 5 speakers, 6 speakers, if you create any arrays of speakers of point source, then you will multiply the interferences. Okay, so you have many interferences that happens now, and this is a typical situation of what happens if you, for example, have different point source with a very big distance between them. Okay, so very inconsistent, very much inconsistent, not consistent coverage on the audience. So just to summarize, point source, they are you cannot make any arrays with point source, and then what we can say also is that we lose energy 6 dB per doubling distance, and this is omnidirectional in the low end, and it becomes directional in the mid-range. Let's have a look now to straight line source. So let's make the same experiment, but instead of using point source, we use a line source. So what is a line source? Is a source where the energy is not emitted from a point, but along a line. Okay, so this is a line. In our industry, we have dedicated cabinets that can be used as a line source. So once again, if I look in my NS1, so let's move to NS1 again. Let's go with M28. Okay, so this is our line array. And if I look from the side of a line array, this is speakers. So this is spatial speakers. And these are not point source. We have waveguide inside. So these are spatial speakers. But if I put the speakers right on the top of each other, then I can create a line source. Okay, this is the same. This is more or less the same. So this is my experiment. What is a line source? What is the behavior of a line source? So let's go back to my PowerPoint again. So what is the difference between a point source and a line source? Is line source is not creating now a spherical wavefront, but is going to provide a cylindrical wavefront. So this is a cylinder. The main difference between a sphere and a cylinder is when you increase the radius by 2, if you multiply the frequency by 2, then the surface is increased by 2 instead of 4. So the SPL drops now at -3 dB per doubling distance. Okay, so interesting for me, because if I now look at the throw of the system, which will much more efficient using a line source compared to a point source, because the decreasing the SPL drops only of -3 dB per doubling distance. If I look at, for example, what we calculated just before, we saw that if I can provide with a point source, if I provide 130 dB SPL at 1 meters, I will have 100 dB SPL at the mixing positions. But the question now is the opposite. If I use a line source, and let's say that this line source is also providing 30 dB SPL at 1 meter, how many dB SPL will we have, at the mixing positions? If I considered 130 dB SPL at 1 meter, if I multiply the distance by 2, then I will lose 3 dB. So 2 meters goes to 127, 4 meters go to 124, 8 goes to 121, 16 goes 118, and 32 goes 115. Okay, so this is 15 dB more if we compare point source with line source. Okay, so a very high benefit. Unfortunately, we have to go to dig in a little bit, so to go more in depth, because the problem is the cylinder behaviors will stop at a given distance. So there is a limit that we call the limit from near field to far field. And this limit from near field to far field define what we call the near field behavior. So this is -3 dB. And if we go to far field, then the level will drop to 6 dB. Why? Because we keep a cylindrical wavefront in the near field, but when we go to the far field, it will be a sphere, okay? So unfortunately, we cannot provide a cylinder to a very big distance according to the frequency. It depends of this limit. And this limit, you see the formula, this limit is equal to frequency multiplied by length square. So length is the length of the line divided by 2 times the speed of sound. So when you are in the far field, this is the inverse square law that apply. So this will be -6 dB per doubling distance. If I, for example, have an example, so we have a line array. This line array is 4 meters, so the length is 4 meters. I calculate different near field limits for this 4 meters straight line source. So I can see that at 250 Hertz, the limit is 5.88, so around 6 meters. So this is the limit. Okay, so you see it's very short distance in the low mid-range. And if I go now to high mid-range, 2000 Hertz, you can see that the near field is 47 meters, so big one, big value. So for people, if you say that the mixing positions, or if you have any people standing right in the middle in the audience at that positions, he will be in the far field for the low frequency, and he will be in the near field for the medium and high frequency. So different behavior. -6 dB, so less low frequency at that positions because I have more dispersions, and more high frequency in this position because I have less dispersions. This is only -3. We'll talk about that later. So keep in mind, this is very interesting, a little bit more complicated, but this is a very interesting point that we need to remember. Let's have a look now to the coverage of the line source. So let's move back to NS1. Let's have a look to the behavior of the line. So if I right-click on the screen, I can visualize the sound pressure level given by my line source. And you see that this sound pressure level, I will try to emphasize the value. So you see here, this is extremely directive. Okay, we are in the near field. So this is extremely directive. So what does it mean? It means that for people who are just inside the beam, the level is very nice. But for people who are outside the beams, it's not very good. Okay, it's not very nice. So let's try to visualize again this coverage on the, for example, on a real audience. So this is what we visualize here. So let's assume that this is a cut view. So we have here a standing venue, and this is a seated area. So we have people seated here, and we have people standing here. You can see that this kind of design is very good for people at the right part of the audience. The throw is big, highly directive. So people at that positions are very pleased, okay? But if we now look at the people at that positions, then when I say that position, sorry, I mean this one. So at that positions, the people will not be very pleased because they are not inside the beam. So first, the throw is very important, very big with a straight line source. If I look at the different frequency response, we can see that frequency response depends on the receiver positions. So the frequency response that you see here are calculated for 4 meters, 8 meters, 16, 32. So we have the red curves is for this one, the blue one is this one, and so on, green, purple. we can visualize that in that with a straight line source, as long as we go back at the audience, we lose the low frequency. And the reasons is just because we are now in the far field for the low frequency. And the far field has a dispersions of -6 dB. So important to summarize for us, given a straight line source, you always have a big throw, but also a frequency response that depends on receiver positions. So what we can try to do is try to make, instead of doing a straight line, we're going to curve a line, okay? We're going to make what we call a constant curvature line source, for example. If you go to a constant curvature line source, then let's have a look. Then you can see that we bring the coverage in the first part of the audience. So we have less throw because of vertical dispersions, but the frequency response now keeps consistent over the distance. Okay, so interesting results. We lose the throw, but we make the consistency of the frequency response better. Okay, and if now I do a progressively curved line source, so this is a progressively curved line source, what I can see here is I try to mix and to combine a straight and a curve. So I use a straight line for the top of the arrays and a curved line for the bottom part of the array. And the idea is to mix the two. So I will have a long throw for the back of the audience and a short throw for the beginning of the audience. And if I play and if I do the right shape, then I will be able to provide a constant level along the audience. So this is the first thing. And depending of the number of speakers, depending of the shape of your arrays, it's also possible to get a curvature that will try to make the consistency of the frequency response good along the audience. Okay, so if I want to make my coverage as consistent as possible, so I will try to give different angle value so that these pressure plots will be as flat as possible. Okay, so I will try to do a progressively curved line source and have a look to my curves. Let's do these things. And if I look now at the sound pressure level contour, you see, so I just try to make a shape of the array where the energy is distributed consistently on the audience. Okay, this is what I did. So just to finish and to conclude, when we talk about line array, we also need to take care about air absorptions because as you may know, there are what we call friction forces that apply to the air particle velocity. And what we see is the high frequency as much more absorbed than the low frequency due to the air. These air absorptions will be different depending of temperature of humidity. And this is an example, for example, at 10,000 Hertz, we can see that we have at 100 meters, and this is feet here. So this is 300 feet, so 100 meters. 10,000 Hertz, this is something like 40 dB of attenuation, a little bit less. So it's a very big value for attenuation. And this is an example. So you can visualize this frequency response on VNS1. But if I take, for example, a value of 45 meters deep, so this is the measurement microphone. You can see the frequency response due to the air absorption and 20 degrees, 35% of humidity, and the same frequency response at 35 degrees, 85%. Okay, so less high frequency attenuation. And if I look now at mean and gradient temperatures, once again, we need to think about what we call, what is a temperature gradient? Is a difference of temperatures between the air and the ground. And depending if the air is colder or warmer than the ground, then the sounds can be refracted and go, for example, towards the people or towards the sky. So in our case, these are two examples. Could be an outdoor situation where we have, this is a morning situation. So in the morning, the ground is colder than the air. So in that case, you do the rehearsals, for example, and you can see that the sound is refracted downwards, so which is nice because the people are on the ground. If we do the same experiment on the night, this is the opposite. The air is cold and the ground is warm because we have people now, and the sound is refracted upwards. Okay, and if it goes upwards, this is not as good as a morning because the sound is not focusing on the people. So once again, be careful when you try to visualize when you use the NS1, because atmospheric conditions and air absorptions can quickly change, and then the results above 100 meters are most of the time unpredictable. Okay, it's impossible to make it to do the prediction because of these atmospheric conditions. Right, so I'm very close to the end of our seminar. Looking at the time, yes, this is 11:55. If you have any question, you can ask your question in the Q&A value. Maybe before we leave, I can take the time just to give you some information. We have, so if you have any question, yes, this is this one. If you have any question, if you want to ask or to submit any question or anything, please use that email address, which is technical@nexo.fr. So this is an open address when we answer any question. So feel free to ask your question. We also have this address, which is the technical cloud address. So if you go on nexosa.com/cloud, you will access to any technical documentation. You can download everything. It's a little bit it's more faster compared to the website. Okay, so feel free, and we have also other information that are not on the website. So if you need very deep information on our technical documents, feel free to go and connect to this website address. Thank you for attending the webinar. Thank you, Joe. Not too many questions this morning. Huh? Relax.
No, but we do have one now from Santa. Yes, I think they're asking how to do phase alignment on a line array.
Okay, phase alignment on the line array. So we don't have to do any phase alignment on the line array. The reasons is that the design of the cabinets is done that all the cabinets, when they are assembled in a line, they are all in phase. Okay, so it's very straightforward. There are some kind of rules that we need to follow when we design line array, like we need to keep a distance between the two low frequency driver. We need also to design special shape for waveguide. And the benefits of this design, if I put the speakers on the line and do the angles, all the speakers will be in phase. Okay, so I don't have to do any phase alignment. The only phase alignment that I will have to do with the line array is if I have to combine this line array with subwoofer. So in that case, I need to do the phase alignment between the subs and the cabinets. Is the cylindrical propagation also applying to line source like column array speakers? This is more or less the same, except that for column array speakers, in some column array speakers, sometimes we don't have the waveguide. So a column array speakers can use electronics just to provide the beam width of the arrays, or on the opposites, can be very small waveguides in the driver, or if we do not exceed a given frequency, then we don't have to use a sophisticated waveguide on columns. And that's it. No open question.
No. I need to go. Thank you,
Okay,
everybody,
thank
for
you very
joining
much.
us.
Yeah, Joe. So Joe has a meeting now. So guys, thank you again for attending the meeting. Thank you, Joe. See you next
Thank you,
time.
Nicolas. Yes, see you soon.